So we've discussed Charles' law, Boyle's law, the combined gas law, and now we're going to talk about Avogadro's law, which really relates volumes and the amount of substance that we have in moles. So it looks like Avogadro found out that volume is proportional to the number of moles that we call N here. Okay, and so by the same logic, this means that volume is proportional to something constant times n. So if we just replace the proportional sign with equals, we can divide the n's here, and we'll find that volume divided by the number of moles will always be constant. Hence, V1 over N1 will be equal to V2 over N2, because at the end of the day, both of these will be constant. V1 over N1 will be constant, and V2 over N2 will be constant. So that is Avogadro's law here. And we can see an example of that, of how they are directly proportional, because if you exhale air into a balloon, you're adding more molecules to the inside of the balloon, and so it expands, or its volume increases. Let us do an example, and in this example we have a 4.8 liter sample of helium gas that contains 0.22 moles of helium. How many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liters? Okay, so what do we have? We have volume 1 to be 4.8 liters, and N1 as 0.22 moles of helium. And then how many additional moles of helium must be added to the sample to obtain a volume 2 of 6.4 liters. So as you can see, of course, since volume went up, it should make sense that the number of moles should go up. But let's measure exactly how much that is. So let's use this equation. V1, 4.8 liters, over N1, 0.22 moles. And we have V2, that is 6.4 liters, and N2, which is unknown. That would be our final volume, or the final number of moles. Okay, so here to solve for this, you algebraically can multiply both sides here, and then move this to the other side by multiplying by its reciprocal. Okay, so you can see that the liters cancel, so I'm just going to multiply everything here, which is 6.4 times 0.22 divided by 4.8, and so I ended up with 0.29 moles as my final volume of helium. But pay attention to this, because this was in the original container, and I wanted to see how many more moles of helium I must add. So this is my final volume, or I'm sorry, my final number of moles. So to see how many additional moles of helium, I had to do the difference between those two. So it'll be 0.9 moles minus 0.22 moles. And so that will be 0.07 moles of helium must be added additionally to my original container in order to achieve this volume. Okay? Alright, you may go ahead and try this on your own. A chemical reaction in a cylinder equipped with a movable piston produces 0.58 moles of a gaseous product. Okay? If the cylinder contained 0.11 moles of the gas before the reaction and had an initial volume of 2.1 liters, what is its volume after the reaction? So it looks like here that our initial amount of moles was 0.11 moles. Make sure you read that carefully. This was before the reaction, and the volume 1 before the reaction was 2.1 liters. Okay, then we let the reaction go, and we ended up with N2 being 0.58 moles. What is the volume 2? Now, before we do anything else, and I keep asking you guys because these are good conceptual questions to ask you on the exam. If the number of moles increased, then what should you expect to the volume of this container? Because moles and volume are, think about your balloon. When you're pumping more gas into your balloon, you're increasing its volume. So this volume should also increase. But let's set up Avogadro's law, and let us plug everything in to find out exactly how much. So we figure conceptually what's going to happen, and then we figure exactly the quantity of that. So we are trying to solve for V2 here. Now, a lot of people, I like to plug in numbers first, like I keep telling you guys, and then solve for V2, but you can just find out what you need to solve for and move your variables around if that makes it easier for you. So let's do it this way. You'll just multiply this like that. So your V2 is going to be your V1 times your N2 over your N1. You can do that kind of thing too. So whatever works for you in terms of algebra. So let's plug everything in. And N1 is 0.11 moles. Notice the moles cancel, and my answer is going to be in liters. So what's 2.1 times 0.58 divided by 0.11? That would be 11.07. And it looks like we have two sig figs here, so we'll just call that 11 liters. And you can see that, yes, it did go up. And look at this. This went from 0.1 to about 0.58, so it increased roughly by 5 times. So this should be roughly 10 point something, right? Because it should increase roughly by 5 times. So you can even estimate how much the quantity is, all right? Okay, let's do a conceptual checkpoint. If each gas sample has the same temperature and pressure, which has the greatest volume, and we're given the number of grams of oxygen, argon, and hydrogen, 1 gram of each. Alright, you may think, okay, well, they all have the same amount of grams, so I'm just going to say, okay, the same amount, then if they all have the same amount of grams, then they should all have the same amount of volume. But that is incorrect, because what Avogadro said, and granted that temperature and pressure are held constant, right? Because Avogadro looked at volume and the number of moles, while temperature and pressure remain constant. Because remember, guys, in science we have to hold some variable constant and see how these two relate to each other, okay? So that's why this would automatically stand out to you as an Avogadro's law problem, because you have the amount, N, and you have the volume, whereas temperature and pressure remain constant. Okay, but like we were saying, Avogadro didn't say that 1 gram of the mass of something is proportional to its volume. He said the number of moles of something is proportional to its volume. Very, very important, okay? So, let's see. We would have to convert the grams into moles. So, and we would have to use molar mass for that. So, that would be 32 for oxygen right there. So, let's see how much. 1 divided by 32 is 0.031 125 moles. And then let's see how much argon we have. We have 1 gram of argon, and argon is 39.95 grams per 1 mole. So you can see this is even going to be a smaller number because it's 1 over 39. So 1 over 39.95 to be exact. So that is 0.0250 moles of argon. And then, I'm going to squeeze this in here, is the hydrogen, 1 gram of H2. And you can see that there's 2.02 grams of hydrogen for every 1 mole of hydrogen gas. And you see it's H2, so that's why I did 2.02. Alright, and you can see it's 1 over 2. That's approximately, it's going to be bigger than these numbers. Alright, so that, again, you should be doing these kind of rough estimates in your head in order to maximize the amount of time that you have. So from these three, it looks like this has the greatest amount of moles, the largest N, so it should also have the largest volume. So largest N, largest volume would be for the hydrogen gas container. So that would win right there.